What should you do about imbalanced datasets in machine learning? Imagine trying to teach a child to recognize rare birds when most of the pictures are of common peons. The child might overlook the rare birds because they are underrepresented. That's what happens with imbalanced datasets in machine learning. When one class has way more examples than another, models tend to favor the majority class and ignore the minority. This can be a big problem in real-world tasks like fraud detection, where fraud cases are rare but very important to catch. So what can you do to fix this? Let's explore some practical steps. First, it's important to choose the right way to measure how well your model is doing. Accuracy can be misleading when data is imbalanced, because a model could just predict the common class all the time and still get high accuracy. Instead, look at metrics like precision, which tells you how many of the predicted positives are actually correct, and recall, which shows how many actual positives your model finds. The F1 score combines both to give a balanced view. Area under the curve, or AUC, measures how well your model separates the classes overall. Using these metrics helps you understand how your model performs on the minority class. Next, resampling techniques can help balance your data. Oversampling involves adding more examples of the minority class, either by duplicating existing ones or creating new synthetic samples. A popular method for creating synthetic data is called synthetic minority oversampling technique, or SMOTE. It generates new, plausible minority class examples by interpolating between existing ones. On the flip side, undersampling reduces the number of majority class examples. This can make the dataset more balanced but risks losing some important information from the majority class. When it comes to choosing algorithms, some models handle imbalance better than others. Tree-based models like decision trees, random forests, and gradient-boosted trees tend to focus on misclassified points and can perform better with imbalanced data. If the minority class is very rare, anomaly detection algorithms are useful because they treat these cases as outliers. They are designed to find rare, unusual instances in the data. Another effective approach is adjusting class weights during training. Many machine learning frameworks allow you to assign higher importance to minority class samples. This way, the model pays more attention to these examples without changing the dataset itself. For example, in some frameworks, you can specify class weights directly, which helps the model learn to recognize the minority class better. Ensemble methods combine multiple models to improve detection of the minority class. By aggregating predictions from different models, you reduce the chance of missing rare cases. Techniques like boosting or bagging are common ways to build these ensembles. Finally, consider how you sample data during training. When working with mini-batches, ensure each batch contains enough minority class examples. You can do this by upweighting minority samples or downsampling the majority class within each batch. This helps the model learn the patterns of the minority class more effectively. Understanding and handling imbalanced datasets is vital for building fair and reliable machine learning systems. Many AI tools like ChatGPT, DALL-E, and Midjourney relying on models trained on real-world data, which can be imbalanced. If these models are biased toward the majority class, they might produce unfair or inaccurate results, especially in sensitive areas like healthcare or finance. To prevent this, always evaluate your models with metrics that reveal how well they recognize the minority class. Use resampling, weighting, and algorithm choices to improve detection. And remember, ethical AI depends on making sure all groups and cases are fairly represented. These steps help create smarter, fairer AI systems that work well for everyone.